All right, let's look at the free response portion, starting with 1980, number 2. I've already written out some of the work, but I want to explain what I have up here. And this is with the goal of getting you to understand and sort of perhaps broaden your idea of what a perfectly inelastic collision really looks like or constitutes. Because a lot of the time, perfectly inelastic collisions don't look like the classic, a bullet embeds itself in a block, or, a ball of putty sticks to some object like a brick or something like that. So it doesn't always involve a splat or something embedding itself in something. It can look like other stuff, like this one, and also like an example that we did earlier in class with, two blocks that have springs on them, right? Where for an instant they're moving at the same speed, and so even though they later spring apart, for an instant it's like a perfectly inelastic collision. All right, so that's actually the idea here is, this and this, they're both, on a frictionless surface. This one, comes and slides into, moves up, and as a result, since, it's not nailed to the surface, it and the block will both begin sliding this way. All right, so really, actually, that is a perfectly inelastic collision because you have two objects that were once separate that are now moving along at the same speed together. There was actually another year of the AP exam, which I have given as a test question before, and I'm not this year, but just for context, right? They gave you a slab on a frictionless surface with a little block on top of it. And then they said the block was, given some kind of a sudden impulse, right? And then after a while, a little while later, this doesn't slide off the end, comes to rest somewhere along the slab, and the two things are now moving along together across the frictionless surface. And a lot of people struggle to sort of place that problem. Like, what, am I supposed to use conservation of energy? Am I supposed to, what's going on here? All right, and it's conservation of momentum because you have two objects which were once moving with their own separate velocities. In this case, this one not moving and this one moving. And then sometime later, they are moved along together with the same velocity. So regardless of exactly what that looks like, if you have two things that were separate and then for any amount of time are moving along together at the same velocity, at that moment when they're moving along together, it's a perfectly inelastic collision, even if that's a very temporary moment, such as it is in this question. All right, now, in this one, therefore, at this first moment that they ask about, if it's perfectly inelastic, momentum's conserved, kinetic energy is not. All right, so that means we're not necessarily going to be able to figure out the final speed of that system using energy. In fact, you won't get it using energy. You will get it using momentum. All right, so that just looks like this. If it's perfectly inelastic, there's your initial momentum. Your final momentum consists of this expression because you have a total mass of 4m moving along together. All right, so the final speed is 1/4 of the initial speed. All right, now that is your answer to part A in a nutshell, very, very briefly. Part B, that one is necessarily going to involve energy, right? If the question is, how high up does this go before it comes to rest? You're not going to get there with kinematics because the surface that it's moving on, that it's going onto is also beginning to move. So it doesn't actually come to rest, which is how you would approach this if it were like a kinematics question or something, right? Is you'd say, well, it goes up and then it stops for an instant and then it's going to slide back down. It doesn't stop. It moves this way during, when it's at its maximum height even, right? It's still translating this way. So it's actually got to end up being an energy thing, which is counterintuitive because we just said it's a perfectly inelastic collision. All right, now, be careful. When we say perfectly inelastic, what that means is kinetic energy is not conserved. If it's a thing embedding itself in something else, then you lose energy to heat, deformation of the materials, and sound. All right, for this one, since there's no friction and nothing's necessarily being deformed exactly, but rather the lost kinetic energy is now being stored as gravitational potential energy, you can say that the total energy is conserved and therefore follows this equation right here, that the initial kinetic energy becomes final kinetic energy for the whole moving system plus the gravitational potential energy for the little block. All right, now I do have one mistake here in my expression, and that would be, oh no, what should that be? If you said 4m, you are correct, right? Because the mass that's moving, that has kinetic energy at that moment when they're moving along together, is the whole system, which has a total mass of 4m. Okay, so now I could go ahead and plug in my final velocity into that, and then do some algebra, and from that determine what the maximum height is. All right, I'm not going to bore you with the algebra. You have the answers published for you, but that would be the process to get to that answer, right? Plug in, work it out, and ultimately you'll end up with an expression for the maximum height in terms of the initial velocity and g. All right, now, after it slides back down, because it's going to do that, it has its own velocity. All right, sorry, I should have said v1f, whatever. They each have their own final velocities. And so that means now this is an elastic collision. All right, now again, it doesn't look like most elastic collisions. Most elastic collisions look like, you know, two pool balls collide or something and they bounce off. And this doesn't look like that. That's okay. It fits the definition of an elastic collision. Momentum's conserved, all right, because there's no significant outside forces. And kinetic energy is also going to be conserved because there was no work being done by outside forces. Yeah, I mean, and also, you know, they're not like sticking together or something like that. So let me see. Yeah, they don't necessarily say it's elastic, but we can presume that this stored gravitational potential energy all comes back and turns into kinetic energy of the system. Also, if you had further doubts, right, you could say, well, like, look at it. There isn't anywhere else that energy could have gone, right? It's got to all be in the form of kinetic energy. All right, so then the process here would look like, all right, V1 final equals V naught minus 3V2 final. Then that would get plugged in over here into your conservation of energy. All right, so the 1/2s and the m's are all going to cancel out, except for the factor of 3 there, since the ramp is 3 times as massive. All right, so we'll have V naught squared equals, all right, V naught minus 3V2 final squared plus 3V2 final squared. All right, don't forget this has to be FOILed out. So what it should turn into is V naught squared minus 6 V naught V2 final plus 9 V2 final squared plus 3 V2 final squared. All right, now what this is going to end up giving us is that the final velocity of, well, of something is V naught over 2. All right, so then what did we just figure out the final velocity for? Oh, well, we found the final velocity of the ramp, right? Not of the block, which is what they were asking about, okay? All right, if you're not down on the algebra there, I'm combining like terms. These two will cancel out entirely. When I move that over to the other side, it will become a positive 6 V naught V2 final. So we should get 6 V naught V2 final equals 12 V2 final squared. One factor of V2 final will cancel out. All right, so then we get V naught over 2. All right, so to get the speed of the block, we now plug this back in here. It's probably the easiest way to get that. And so now we have that. And we get that the final velocity is negative V naught over 2 for the block. All right, so it's moving half as fast as it was before and in the opposite direction. All right, I think, yep, that's all parts of that particular problem. All right, time for second free response question.